This is ECE 4960, Spring 2023, and our group did a CNC photo creator. This project is to create a CNC machine that processes image from a GUI to a pen-on-paper drawing completed within a semester, costing around $200. And it was completed by Deeb Armali, Patty Broomfield, Ryan Mercado, Carrie Nelson, Hannah Roberts, and Brandon White. So as stated, this machine will upload a given image through a GUI and read the image through image processing and translate it onto a piece of paper. The inspiration for this project was brought by the Cricut machines, and we wanted to create a project that could later be implemented and translated to a woodcutter, a laser cutter, or anything of that sort. So the requirements for this project were less than 1 amp per motor and a 12-volt power source. And the only constraints currently are that the GUI only accepts PNG and JPEG images, and this is based off of popularity with file types that users have. This project was broken up into 3 milestones. The first milestone was mainly getting the motors moving. The second milestone was having the base constructed and having all 3 motors being able to move at once and being able to draw a triangle, square, and a circle. And the final milestone was that the GUI can upload any image, take the outlines, and draw it onto a piece of paper. This shows 1 motor moving, and it was an early stage process of the project. This slide shows our prototype. On the left there's a picture of the motors, and the right is the final image from above. There will be a video later on showing how it works.
This is a block diagram of the hardware implementation of our prototype. So basically we run software off a laptop that sends code to a PIC32 microcontroller, which controls the motors on our physical hardware prototype, which will draw the image on a piece of paper. This is a list of all the hardware components we use as part of the project.
This is a flowchart that represents the firmware design we use for the project. So the firmware was written in C, and it is the code that programs the movement of the motors. It starts by accepting a PWM input, and then it checks to make sure the pin is at the home location, and if it's not, then it moves the pin to the home location. Otherwise, it starts drawing the image that was inputted, and then once it checks to see if all the regions has been drawn, it returns to the home location. And of course, there's an e-stop to interrupt if something goes wrong. This is a flowchart representing the software design we used. So we programmed a GUI in Python, and in this GUI, it took the inputted image and converted it to grayscale and created contours. The contours were found using Gaussian algorithm and Canny algorithm, and then it converted it to an SVG file and resized the image. Once it resized the image, it used Bressenham's line algorithm, which allowed the outputs of the GUI to be in a readable input for the motor controllers that were read by the PWM signal.
So this is a brief overview of how the project actually works. So the laptop runs Python code, which uses image vectorization to convert the image into PWM signals. These PWM signals are sent to the PIC32, which tells them how to control the motors.
So based on the datasheet for the motor drivers, we used this equation to determine that we needed less of 1 amp per motor of current. And from this, we are using a 2.5 amp current limit as well as a 12-volt power supply.
This slide shows the circuit diagram for the PIC32. On it, you can see the connections to the motors. You can see directions for X, Y, and Z and the speeds of X, Y, and Z. And those go up to a different diagram that's not pictured here.
This is an overview of how the firmware and software are set up. So for the GUI, we used tkinter as the function, and for the PIC32 code, we used PySerial. And for the motor movements, we calculated it using a distance formula shown here.
This slide shows the equations and values used to convert from angular distance to linear distance, meaning the steps in the motors to the millimeters in distance.
This video is part of our milestone 2 demonstration, where the machine is drawing a triangle on a piece of paper.
This slide gives an overview of our results. The performance was as we expected, and we met all of our goals except for we were unable to automatically switch the colors. It's pretty reliable, except for sometimes it can be off by a few steps. just based on the movement of the motors. In future plans, we would like to implement a laser cutter or a knife or engraver. And in order to maintain it to be as accurate, you will need to replace the belts eventually because they get too loose.
Here are some of the challenges we faced during implementing this project. Some notable ones are deciding what's the best way to implement the image processing using Python. Also, having to reprint some of the 3D parts that we used because they weren't exactly fitting together right. And also just imperfections in some of the components that led to some of the rails being slightly off, and that messed up a lot of the motor drawings. Here are some future directions we have in place for our project. First is being able to change out the pen so we can use multiple pens to draw in different colors. Also, we have plans to use an X-Acto knife or a laser cutter in place of the pen. The modular design of our system makes it relatively easy to change out the pen holder for an attachment for a knife or a laser cutter.
Overall, we successfully created a modularly designed machine that can draw the images after being uploaded. We strayed from the original design of having a pen holder with a servo motor that could change the colors, but this could be in the future directions as mentioned. Some things we learned are that our ambitions were too high with switching colors, and our first milestone had too many requirements that we weren't able to achieve. And we also learned how to adapt quickly and fix and reprint pieces and adjust to change, like fixing the belts and rewiring blown components. But overall, our project was a success, and the team is very impressed with our work.
This is a video of our final demo. A tiger ball was uploaded to the GUI and then converted to SVG code. SVG code means that it is written region by region and not line by line, like a printer. The regions are drawn by area, so the biggest area is drawn first and then goes on to the next areas until it's completed, and then it returns to the home that was set for the prototype.
A huge thank you to the ECE department and Dr. Raza for the funding and help for this project. These are the references we used throughout the project.
Go Tigers!